Welcome back to week 7, and in video 2 we are going to talk about how we measure earthquakes, what the scales that we use to measure earthquakes exist, and what the more popular or more accurate scales are, and how we locate the epicenter of an earthquake. So how do we measure earthquakes and what scales exist? Well, the equipment used for measuring earthquake intensity and magnitude has changed over the years. The basic setup you can see here, where we have a drum that is rotating constantly that's attached to the bedrock, so to the crust that's going to be moving around. And then what we have also is an arm with a spring attached to it that is free to move around. And then we have this weight and a drum or a pen that's able to write, so that pen is going to stay stationary while the drum rotates and moves underneath it. So you can imagine you've got to have a couple of these set up in various orientations. Now, instead of a pen writing on actual paper, a lot of these are actually digital, so they don't need to have pen and paper. They don't have to replace the paper all the time or replace the ink all the time. But what ends up happening is, as this rotates over and over again, you can see here, this is in Puerto Rico in, let's see, 2003, and this is an old recording station where it's showing you the data that's been recorded on these drums for various locations around Puerto Rico. And so here you can see a massive earthquake that occurred. Sometimes this information might not be accurate if these are placed in areas that are close to populated areas, like next to a highway. You can get truck traffic. You can get actual people walking if it's not put in the correct location. So these need to be placed in appropriate locations. So once we get this information, so basically the bigger the swing of this graph here, the bigger the earthquake. So you can see pretty calm areas, and then boom, huge amounts of activity. So what are the scales that we used? Well, one of them is called the Mercalli Scale. This is the oldest. It's based on damage to man-made or human-made structures. Started in 1902. This scale requires little instrumentation, but it needs to have some kind of human structure or observations to be able to actually give you a number on this scale. If no one is around, no one feels it, you don't have a structure present to observe damage, or there's no features around to be able to say, hey, this is what I observed after this earthquake, then you can't really place a number on it. But basically what you have here is from 1 all the way up to 12, and you can see here how the Richter scale that we're going to talk next, how that compares to these observations. But basically we can go from 3, which is felt noticeably indoors, not always recognized as an earthquake. Standing cars maybe rock slightly, like a passing truck, vibrations produced from that. If we go to, say, a 7 here, people run outdoors, damage to buildings may vary. You see people driving around notice it. If we move up to a 9, buildings shift off foundations, cracked, thrown off of foundations, ground cracked, pipes broken, and then all the way to the very highest here. Waves seen on the ground surface, line of sight, level distorted, objects thrown up in the air. So this is all based on observations. Next one is called the Richter scale. This is based on the amplitude of a seismogram. So if you look at this seismogram here, we have the pen moving up and down, and all of a sudden, boom, lots of shaking, and then it dissipates. So the amplitude would be the highest point to the lowest point. So here you can see, or sorry, not the highest to the lowest. So going from a normal situation and measuring to the highest point would be your amplitude. And this was established in 1953. This Richter scale it's great for measuring seismic energy, but not the impact of the earthquake. Some drawbacks is that this is based on old equipment developed for California type earthquakes, and it maxes out at 7.0. So if we have a bigger earthquake than that, there's no way to tell, we just know it's greater than 7. and it's not great for distant earthquakes. So this isn't a great use, but it is still used in some areas, because if you're using old equipment and you're not worried about earthquakes over 7, then you're fine. But when you're trying to expand your reach here, then things kind of get outdated. So what was the most accurate and most common way to get an actual number for these earthquakes? Well, we have the moment magnitude scale. This is based on lots of different information. So geologists will actually go out into the field and take measurements. So they'll go out, say, to this picture here, this image, and say, okay, well, we know this road was once connected on either side of this fault. So they can go and measure how much that road has been offset by the fault. So you can measure the length of the fault rupture. We can measure the depth of the rupture. So you can go out and say, okay, how deep does this rupture go into the ground? We can measure the total amount of slip on that fault, which is that number I gave you before. The fault rupture would be where you see it on the Earth's surface, and then measure the rock strength. So this is great because it allows scientists to measure the amount of energy released. You can get really accurate numbers, but it takes some time because it requires geologists to actually go to the location, make field observations and measurements. So sometimes data like this you might hear on the radio, you get a number out that's based on the Richter or the Mercalli scale, and then it changes. After a few days, scientists have a chance to go out and take some measurements, and they realize, oh, it's much bigger than we thought, or it's lower than we thought. Usually it's much higher than they thought, because these other scales here, like the Richter scale, maxes out. The Mercalli, based on observations, so sometimes that can be thrown off a bit based on where you are, what type of bedrock are you on, or on loose gravel, and so things can change that way. So those are the major scales. Your book goes into some good detail, so check that out. And then the last thing is I want to talk about how we locate the epicenter of an earthquake. Now, P and S waves travel at a set speed. We know how fast they move, so we can plot based on all the information we have from earthquakes. We can create these graphs. So we know we got the P wave travel time graph, so we can figure out how long it takes it to go a certain distance. S wave, same thing, and every time they take any data, it plots on these graphs every single time. So we use those to tell us how far away you are from the epicenter. So basically what you do is you're at a station and we get an earthquake wave that hits. Your P wave is going to be the first because it travels much faster. S wave is going to be second, so you can measure how much time passed between those two waves. And then we go back here to your graph, and then we see, okay, where on this graph is the same time difference between those two lines. So let's say we determine that it's about this point, we follow it down, we know we're 500 kilometers from the epicenter. But we don't know which direction, so we can draw a circle on a map. So if we get 3 different stations at least, then we can triangulate usually these 3 different stations and the distance those epicenters are, or those stations are from the epicenter. We can draw these circles, and then where they overlap tells us that's where our epicenter would be. So you, in lab, you can either use the online program to draw these circles, or you can use a protractor to be able to, and a compass to draw those circles in lab. So that's measuring earthquakes and epicenters. So we'll come back and talk about effects of earthquake activity and how this relates to the interior of the Earth.